Okay, so today we're recapping a skill we did in Year 11 in Semester 2, and it will just be a little bit more complex because we know more complex differentiation. And what we're talking about is when is a function increasing and when is a function decreasing. And the best way to think about it is that you're always walking along the function from left to right, just like how we would write on a page from left to right. So we're walking along the function from left to right. If I'm walking along this function, I would be walking uphill. So I can look at this graph and know that I'm increasing until I get to x is minus 2. All right? So if I'm going to talk, this isn't in the notes book by the way, this is just a sort of preliminary explanation. I'm increasing until for values of x that are less than or equal to minus 2. We always include the point. Okay? And then after minus 2, I would be walking downhill. The function is decreasing. So we can see it's decreasing between minus 2 and positive 5. We're always talking about x values because we're always moving along the x-axis, okay? Increasing, decreasing. And then after x is 5, okay, we're increasing again. We will be walking back uphill. So what we're doing today then is we're going to be answering these kind of questions but using calculus techniques. What we should recognize is that if I'm walking uphill, if a function's increasing, that means it has positive slope. If I'm walking downhill, a function has negative slope. So here's what we're going to do today. We start with the function, we find its derivative. Okay, we find the slope function and we draw the sine diagram. This sine diagram is going to tell us when it has positive slope, when it has negative slope, and hence we can answer when it's increasing and decreasing. So let's start with the first one. Here's our process. First, we differentiate it. So the derivative of x squared take 4x will be 2x take away 4. So we find the derivative. We're going to draw the sine diagram of the derivative function. Okay? So we will look at calculator techniques in a moment, but this is something I wouldn't be able to expect you to do manually, okay? If I'm going to graph this function, by the way, here's what it'll look like. It's the equation of a line, all right? It has a y-intercept of minus 4, so that's where it crosses the y-axis, minus 4, and it has a slope of 2. That means it goes across 1, up 2, across 1, up 2, across 1, up 2. So it's going to be like that. Okay, so that's x is 1, that's x is 2. And so if we're drawing a sine diagram, on the sine diagram we put the zeros and the asymptotes. The zeros are the roots. The roots of the equation are the values that make it equal to 0. So if we make this equal to 0 and solve it, we have x equals 2. Which is our x-intercept, okay? That's what we expect. It's what we see on the graph. That's what we see when we find the 0, the roots of the equation. We have a root at 2. And from the graph, okay, we can see that it is below the x-axis before 2. It's below the x-axis. And then after 2, it is above the x-axis. So it's positive after 2, and it's negative before 2. So this is the sine diagram of, I'm going to write here alongside it, f dash of x. Okay, that's the sine diagram, or dy on dx, I should say, given the notation. All right, now we're using this is the slope function. It tells us about the original function. What this means is the original function has negative slope for values less than 2. What does negative slope mean? It means you're walking downhill. You're decreasing. So our original function, we're making comments about our original function. Our original function is decreasing for values less than 2. And then following that, it is increasing for values larger than 2. Okay, positive slope for values larger than 2. So that's a really easy example of what we're doing here today. We're finding the derivative, we're drawing its sine diagram, and then based off the sine diagram, we make comments about where it is increasing and where it is decreasing. Okay, for question B, we're going to do that one on our calculator. We're not even going to differentiate it. and we will change this function a little bit as well. So if you've got b there, b says x squared take 5x, and I'm going to change it to take 3, not take 36. Okay, so you just cross out the 6 on there. X squared, take 5x, take 3, on top of x plus 2. This is the function that we're given, and we want to know when is this function increasing and decreasing. Now, as far as technology goes, we could just graph it and look at the graph and observe it. So let's start with that to begin with. Let's start with how we can just use technology to look at the original function. So we're going to graph this one. I've got my handy dandy upgraded emulator here. X squared take 5x take 3. And then at the bottom I have x plus 2. So if you've got your calculator, follow along. I won't go too fast. Alright, so I'm just graphing the function. And we'll just change our V window to standard again. So we've all got the same V window. And we might need to zoom out a bit more because there's a bit of that graph missing. So let's set our V window from -20 to 20. Now in a test situation, test and exam, we are always going to give you an axis. Alright, we're always going to give you an axis, which means you just put in the V window we're providing you with. Alright, when we're dealing with textbook questions, we may have to fiddle around. I've just pressed the down arrow so we can see it a little bit better there as well. And I'm going to sketch it here just so that I can point to it. So we've got an asymptote here, and it's going like this, and it's going like this. Okay, so if we're talking about when's it increasing, when's it decreasing, all right? We always start from the left, and we can see we're going to be increasing until we get to this point here, all right? And what is that but a local max? And so we can G-solve that local max, okay? Gives us an x value of -5.13. Okay, so we'd be increasing until we get to -5.13, and then we're decreasing. Now, we can sort of see the asymptote on the graph, but we can also know there's going to be an asymptote here because asymptotes occur when the denominator is 0. So we have a vertical asymptote at x equals -2. If we put -2 into this equation, the denominator is 0. We can't divide by 0, and so we have a vertical asymptote there. So what we could see is increasing till we get to 5.13, then decreasing, okay? Then there's an asymptote, then it's going to be decreasing until we get to this point, and then increasing again. We can G-solve that local min. So we can get all that information just from the original function, just from the graph, okay? Let's look at how we can use calculus techniques on our calculator to get these answers. So we can find the derivative of that. We'll skip that step for now. Let's instead draw the sign diagram of the derivative function, okay? And I'm going to do that just by graphing the derivative function. We can graph the derivative function without even finding the derivative. So let's exit out to the graph mode. And we'll follow along here. We're going to press Option, Calc, D on dx. And I want to graph the derivative of y1. I want to graph the derivative of the first function. So I put in y1 because you can see y1 equals. Okay? Now before we graph both, we'll just unselect the original function. I'm only interested in the derivative function at this stage. Okay, so I'll just explain that again. What do? I press Option, Calc, D on dx, and then I typed in f1 corresponds with y, and then I press the number 1. Okay, anyone still a little bit stuck? I'll come see you now. Excellent. Okay, so let's graph that then. I've unselected y1, so I'm only graphing y2. And there's what it looks like. And that's good. Okay, what we can see the asymptote, and we can see that it has 2 roots. Okay, so I want to get this information from this graph. There's an asymptote at -2, and the roots, we can get the roots by g-solving the roots. -5.31. And press the across arrow to get the other root. 1.31.
Thank you.
Okay. Now, the asymptote, we can get that by 2 means. We can observe it, okay, by tracing along it. Okay, I know there's an asymptote at -2. I also know if I differentiate this function, I've got u on top of v. When I differentiate a quotient rule, what's at the bottom? V squared. It's just going to be that component at the bottom squared. So I still have an asymptote when that denominator is 0. So that's how I'm anticipating that's where the asymptote is, but we can also observe it by tracing along and seeing that it gets close to that point. Now here's what we're doing though. We're going, when is it positive and when is it negative? We're not looking at when's it increasing, decreasing. This is the derivative function. We are just looking at when is it above the x-axis, when is it below. It's much easier to observe. So we can see it's above the x-axis before -5.31, okay? It's just above the x-axis, then it goes below the x-axis, then there's the asymptote, it's below the x-axis, and then it is above the x-axis. Now this is a really important pattern here. Look at this. This is the sign diagram of the derivative function. So it tells you when the slope is positive and when the slope is negative. Look at the graph of the original function. We have positive slope until we get to 5.13. Positive slope. We have negative slope between that and the asymptote. Okay? Decreasing. Decreasing. Alright, walking downhill and then increasing. So you can hopefully you can see that connection. The slope function sign diagram tells you when we have positive slope and negative slope. So now we can answer, what are we doing it for? When is it increasing? When is it decreasing? So it's increasing when the slope is positive, all right? So we'll say x is less than or equal to -5.31 and x is greater than or equal to 1.31. All right, positive slope there, positive slope there. Okay, we include those points to demonstrate that it exists at those points. And then it's decreasing when it has negative slope. So that's this interval here. Okay, something to be very clear about. Very particular with my notation there. Okay, look, it exists at -5.31, so we include that point. But it doesn't exist at the asymptote, so we don't include that point. It's decreasing right up to that point, but not at it. Okay, so that's the first interval over which it's decreasing, and here's the second one, 1.31. Okay, again, it exists at 1.31, it doesn't exist at -2. So need to be clear, in a test situation, we're going to be looking, marks are going to be allocated for using the correct notation there. All right, so that's that's how we can use our calculator, right? And in these questions, what you'll do is you'll start with we'll start trying to do them just using manual techniques, but we are going to have our calculator from now on to support us. Use the graphics calculator to draw the sign diagram for you, even if you don't find the derivative function. Okay, last one, this will be a quick one. So we have the function y equals, or f of x equals, e to the x. Okay, so our process, let's do this one manually as well. Find the derivative and draw its sign diagram. Okay, so for its sign diagram, we're going, well, what are the roots? What are the roots? E to the x does not equal 0. There are no roots. All right, it's completely above the x-axis. If you remember the graph, it looks like this. And so it's completely positive. All right, and so this function e to the x is increasing. There's two ways we can say it. Okay, if you want to, you can just say increasing for all x. The correct mathematical notation is increasing x e r. X belongs to the set of all real numbers. All right, so you guys are going to open up 3b. We'll start with question 1, and then we'll move on to question 3. Skip 2 for now. We can talk about that a bit later on. But yeah, question 1, and then on to question 3.